Hello everyone, welcome to our talk, a deep learning method for 2D image stippling. I am Zhongmin from Nanjing University of Science and Technology, and this is a joint work with Beibei and Lei. Stippling is an interesting art format. In computer graphics, digital color stippling produces colored points with a certain distribution, like blue noise distribution, from an input color image. Here is an example for stippling. On the left is the source image. On the right is the stippling result produced by Ma et al. Generally speaking, a stippling is composed of a large number of random points, where these points meet a certain distribution. By controlling the color and size of each point, the visual effect of these points is similar to the original image at a certain distance. There have already been many stippling algorithms currently. All of them are not learning-based methods. Some of them can be summarized as optimization-based methods. These methods starting from a randomized sampling and iteratively adjust each point to proper location. Poisson disk stippling methods avoid iterative optimization and have better randomness than previous category. This category used precomputed tiles for online generating points. It can achieve real-time performance by sacrificing the blue noise property to some extent. However, all of the above are gray image stippling. They only produce grayscale dots. We first extended the traditional single-class Poisson disk sampling to multi-class sampling, which can be used to color stippling perfectly. This method produces pretty good results, especially in perspective of spectrum, but the cost is still expensive. Ma et al. Proposed a fast digital color stippling algorithm. It is able to produce high-quality stippling at real-time performance, but some patterns may be noticeable if points are numerous. Since traditional algorithms have their respective drawbacks, meanwhile, deep learning has been widely used in image synthesis and stylization. We look to deep learning methods for a better solution. Here is the overview of our solution. We propose an encoder-decoder framework for 2D image stippling. It takes the image as input and produces a 3D point set. We use a 3D point set as our output rather than a 2D image, since the point set is more precise and flexible to represent stippling. After that, a post-process is needed to get better results. This is the detailed architecture of our network. We first use a ResNet 50 as an encoder to extract the feature of input image into a Latin vector. We adjust the 40 connected layer in ResNet to fit with the channel number. Then we employ ADA-in decoder to transform the Latin vector to points. The decoder consists of two components, a grid decoder and a generator. The grid decoder decodes the input Latin vector to another Latin vector represented as a grid. We can simply consider that the grid divides the output space into cells, and each cell is a Latin vector containing the information of points in it. The generator transforms the Latin vector to points. More specifically, the generator includes two MLPs, a point density MLP and a point location MLP, to generate point density and point coordinates from the latent vector respectively. The density estimator MLP predicts whether the cell is empty and the point density in the cell. These information are fed to the location MLP to produce the number of points and their coordinates in each cell according to the input point count. In the end, we do a projection on the generated 3D point set to get 2D stippling. The third dimension of points are translated to a specific color value according to the same rule in the dataset. The loss function of our network have two components. The first is content loss. It drives the network to generate results accurate in content. In stippling case, that means color of points are accurate. The second is distribution loss. It constrains the distribution of generated points. We hope the results can follow Brunoise distribution. Before that, we need a dataset as reference to calculate loss value. It's difficult to get large amount of stippling results created by artists. Considering both quality and performance, we decide to prepare our stippling reference using Ma et al.'s real-time algorithm. There are only a few colors used in the stippling, which we call a palette. Color of each point is selected from this palette. We use RGB-CMYK palette throughout our experiment. For each color, we assign it a value, so a point can be saved in a 3D format. That's the basis of our loss calculation. Because the coordinates are normalized to minus 0.5 and 0.5, we choose 7 values in this range evenly. Chamfer distance is a commonly used distance metric between point sets. For each point, the algorithm of chamfer distance finds the nearest neighbor in the other set and sums the squared distances up. Although simple, chamfer distance produces reasonable high-quality results in practice. Spectrum of point sets can reflect the distribution more rigorous. We calculate the difference of spectrum between results and a standard Brunoise distribution as our distribution loss. In practice, we use a 1D form radial spectrum instead of 2D spectrum because we find it hard to converge during training if using 2D form. It is difficult for network to produce a perfectly even point, while the overlapped points in stippling influence the visual perception significantly. Therefore, we designed a point removal algorithm as a post-process to further improve the quality of stippling results. We divide the output space into a grid. For example, we prepare an 8x8 grid. Then we put points of original stippling results into the grid one by one and check overlapping situation in it and its neighbor cells, and remove the overlapped points. The overlapped points are dropped with equal probability. After that, we get a stippling without any overlapped points. Then we will show some of our results. First, we compare our results with two state-of-the-art traditional stippling methods. Overall, our result has correct color, and the distribution of points in our result is relatively even, although it cannot reach the blue noise distribution. Wei's method can't produce good result at this number of points, and it will take quite a long time if increase point number to get better quality. We also perform an ablation study to show our method is effective. In the middle, we directly output 2,500 points without removal. We can see that there are many overlapped points and the distribution is unacceptable. On the right, we output 5,000 points and then perform our removal algorithm. The result becomes close to reference visually. Here we show a close-up view to see the distribution. Without spectral loss, the stippling results look more randomly distributed. With spectral loss, the spacing between points are more even, especially at where the color is smooth. Our method has several limitations. It's hard for color stippling to hold a blue noise distribution, but our distribution is still not good enough, although the visual effect is acceptable. Second, our network depends on the point counts in the stippling, which leads to dataset regeneration and retraining when changing the point count. If we force to increase the point, the distribution becomes in a mess. Now let's conclude our work. First, our work is the first deep learning method to transform images to stippling. Second, we use radio spectrum as a spectral loss to control the distribution of points. And an efficient algorithm is proposed to refine the stippling results. Our result can't guarantee the blue noise spectrum currently, so in the future, we think a better decoder could be helpful to this problem. We also plan to extend our method to 3D stippling. Thank you very much for your attention.